Hello everyone, myself Dr. Pradeep Kumari MR, working as Assistant Professor in the Department of Pharmaceutical Chemistry at KLE College of Pharmacy, Hubli. In this session, I will be discussing on the topic polynuclear hydrocarbons. In that, chemistry of anthracene and its derivative. Anthracene. This is the structure of anthracene with numbering. As we could see the numbering here, it is an exception with the UPAC rules. Coming to the occurrence, anthracene occurs in coal tar and is obtained from the green oil fraction. On cooling this fraction, crude anthracene crystallizes out. Next, molecular orbital structure of anthracene. All 14 carbon atoms in anthracene are sp2 hybridized. The sp2 hybrid orbitals overlap with each other and with s orbitals of the 10 hydrogen atoms forming carbon-carbon and carbon-hydrogen sigma bonds. Since the bonds result from the overlap of trigonal sp2 orbitals, all carbon and hydrogen atoms in anthracene lie in the same plane. This image represents the pi molecular orbital structure of the anthracene. Coming to the resonance structure of anthracene. Anthracene occurs in the following 4 resonance forms. These resonance forms are obtained due to the delocalization of electrons. Coming to the synthesis of anthracene. The first synthesis is Haworth synthesis. This involves the treatment of benzene with phthalic anhydride in the presence of aluminium chloride to form orthobenzoyl benzoic acid. This is then heated with concentrated sulfuric acid to give 9,10 anthraquinone. Further, distillation of the anthraquinone with zinc dust yields anthracene as the final product. Next method is FRIEDEL-CRAFT'S reaction method. There are 3 different ways by which anthracene can be obtained by FRIEDEL-CRAFT'S reaction. First one, benzyl chloride reacts with itself, that is 2 moles of benzyl chloride undergo reaction with each other in the presence of aluminium trichloride to form 9,10 dihydroanthracene, which readily loses 2 hydrogen atoms to yield anthracene. Next, In the second method, anthracene is prepared by the reaction between benzene and 1,1,2,2 tetrabromoethane, which is also known as acetylene tetrabromide. In the third method, benzene undergoes reaction with dibromomethane to initially form 9,10 dihydroanthracene, which readily loses two hydrogen atoms to form the final compound of our interest, that is anthracene. The third method is by the Elb's reaction. First, let us know what is Elb's reaction. The conversion of a diaryl ketone containing a methyl or methylene group ortho to the carbonyl function is known as the Elb's reaction. Here, orthomethyl benzophenone, when heated at 450 degrees centigrade, anthracene is obtained. Here is the reaction. As we could see, orthomethyl benzophenone, when it is heated at 450 degrees centigrade, it gives rise to anthracene as the product. Next, Diels-Alder reaction. Here is the scheme of this. This involves the reaction of 1,4-naphthaquinone with 1,3-butadiene. The product of this reaction is oxidized with chromium trioxide in glacial acetic acid to form 9,10 anthraquinone. Further, distillation of anthraquinone with zinc dust yields anthracene. Now, the different types of the reactions which the anthracene undergoes. Addition and electrophilic substitution reactions. Anthracene undergoes addition and electrophilic substitution reactions. In these reactions, preferentially, the attack occurs at the C9 and C10 positions. Here we are showing attack at C1, attack at C2 as well as attack at C9 with respect to electrophilic substitution reactions. Attack at C9 yields a carbonium ion intermediate in which two benzene rings are retained, whereas attack at C1 or C2 yields an intermediate product in which a naphthalene system is retained. Due to the attack at C9, the intermediate formed is more stable and its formation is more favored because the resonance energy of two benzene rings, which is equal to 72 kilocalories, that is, each benzene ring is having 36 kilocalories energy, exceeds that of naphthalene, which is having 61 kilocalories energy, that is with respect to the resonance energy. This carbonium ion intermediate can lose a proton to give the corresponding substitution product, or it can react with a nucleophile to form the 9,10 addition product. These reactions represents the nucleophilic substitution reaction of the anthracene. Next, reaction with sodium. Anthracene reacts with metallic sodium in liquid ammonia to form 9,10 disodioanthracene, which is deep blue in color. Further, when the disodio derivative is heated with an alkyl halide, here ethyl chloride, it gives the corresponding 9,10 dialkyl anthracene, whereas in this case it is 9,10 diethyl anthracene. Next, reaction with halogen. Anthracene reacts with chlorine in carbon tetrachloride at room temperature to give 9,10 dichloro 9,10 dihydro anthracene, which is an addition product. On heating, this addition product loses a molecule of hydrogen chloride by 1,4 elimination to form 9-chloroanthracene as the product. Next, FRIEDEL-CRAFT'S acylation. Anthracene undergoes acylation with acetyl chloride and aluminium chloride to form 9-acetyl anthracene. Next, nitration reaction. Anthracene undergoes nitration with concentrated nitric acid in acetic anhydride at room temperature to yield a mixture of 9-nitroanthracene and 9,10 dinitroanthracene. The usual nitrating mixture, that is concentrated nitric acid and concentrated sulfuric acid, is not used because it leads to the formation of 9,10 anthraquinone by oxidation. Next, sulfonation. Anthracene undergoes sulfonation with concentrated sulfuric acid to yield a mixture of 1-anthracene sulfonic acid and 2-anthracene sulfonic acid. At lower temperature, 1-anthracene sulfonic acid is obtained as the major product, whereas when the reaction is carried out at higher temperatures, 2 anthracene sulfonic acid is obtained as the major product. Next, reduction reaction. Anthracene undergoes reduction with sodium and ethyl alcohol to form 9,10-dihydroanthracene. On catalytic reduction using nickel at 225 degrees centigrade, first it gives 9,10-hydroanthracene, and on continued hydrogenation it is converted into 1,2,3,4 tetrahydroanthracene and 1,2,3,4,5,6,7,8 octahydroanthracene. Next, oxidation reaction. Anthracene undergoes oxidation with sodium dichromate and sulfuric acid to form 9,10-anthraquinone. Other oxidizing agents like nitric acid and air in the presence of vanadium pentoxide also lead to the formation of 9,10-anthraquinone. Next, Diels-Alder reaction. Anthracene undergoes a Diels-Alder reaction with malic anhydride to yield the corresponding adduct. Use of the anthracene. It is mainly used in the manufacture of anthraquinone, which is a derivative of anthracene. Now we will see the derivative of anthracene, that is anthraquinone. This is the structure of anthraquinone, which contains ketonic groups at 9th and 10th position. So it is having the name 9,10-anthraquinone. There are different methods of synthesis of this anthraquinone. First one, it can be synthesized from anthracene. Here is the scheme. When anthracene is oxidized with sodium dichromate and sulfuric acid or air in the presence of vanadium pentoxide at about 400 degrees centigrade, anthraquinone is obtained as the product. Second method is synthesis of anthraquinone from benzene and phthalic acid. This is the scheme. When benzene is treated with phthalic anhydride in the presence of aluminum chloride, orthobenzoyl benzoic acid is obtained. Further treatment of this with concentrated sulfuric acid yields anthraquinone.